Yeah, so I'll be talking about deep reinforcement. Um, so to get started, why deep reinforcement? Why should you be excited about deep reinforcement? And I guess, to start with the grand claim, I really think this is sorry, lower? Okay. Um, I I really think deep reinforcement learning is the right framework to study artificial intelligence. And I don't mean AI in the sense of, any machine learning system is AI these days. I mean AI in sort of the classical sense of the world, where we're after artificial general intelligence and really trying to build machines that are good at all the things humans are good at, where that spans from, say, driving a car to doing math. So why is DeepRL the right frame? Well, we're not going to settle on a definition of AI, but odd one which uses basically building machines that are good at sequential decision-making systems that humans face. So now if we unpack that, there is no AI without sequential decision. I would say sequential decision-making aspect of the problem is the heart of AI. And reinforcement learning is a general framework for studying such things. So the RL methods we use now might not be the ones that get us there, but reinforcement learning gives us the right problem formulation, whether it's learning and sequential decision. And learning, I think, will harder. So where does deep learning come in? Well, problems that humans face involve perceiving words. And right now, learning is kind of the dominant approach to building machines that perceive them. But I think deep learning is much more general than that. We shouldn't see it as just a feature extract that we, put into our agent. I would say deep learning is essentially a framework for doing end-to-end learning computational graphs. And I think both end-to-end learning and computational graphs will be important. So it's not just about training confidence, it's really about sequential computations and being able to learn in such systems. So again, some examples of this are ConvNets and RNNs, which are popular now. But more generally, if we think about, say, a machine that thinks or ponders about something, then thinking time is essentially another dimension of depth, which is orthogonal to feature extraction depth. And I think a few people have mentioned model-based learning planning. And I think in the long run, we'll have to figure out how to learn models and learn approximate planners, which plan over multiple time steps. That's the important aspect of computational depth. And just as with RL, maybe the current methods that we use in learning will not be the ones that get us there in the long run. But right now, I think that we can be learning basically the area that studies the right problem. So how to learn computation. Deep RL, of course, is not a new thing. Just like deep learning, we're doing it in PhDs. And if anything, it's a slight rebranding of some old stuff, some tricks. So to give a very short and biased history, I think one of the systems that got me excited about machine learning was Jerry Tessara's work on TTCam. So for a long time, this wasn't just the most, I think, impressive demonstration of reinforcement learning. When I was taking my first machine learning courses, I think this was one of the most impressive demonstrations of machine learning in general, not just RL. So back in the late 80s and early 90s, he built a system that basically reached world championship level play in backgammon, self-play and reinforcement learning neural network. This was kind of amazing back then, it still is, but somehow it didn't lead to an explosion of other successive RL events. And I think there are a couple of reasons for that. So the things that were missing were One is computation. So things like AlphaGo, all the work on playing games with RL, they do use way more computation. This is again a parallel with learning. Propagation has been around for a while, but now we have GPUs and train these things quickly. So the other thing is data. Again, in deep learning, ImageNet played a huge role. Was sort of the right data set to both showcase the methods and to learn general representation, which people have been using for other problems. In RL, I think there's just been a lack of interesting domains, environments to work on. So the arcade learning environment, which essentially exposed the reinforcement learning interface to Atari games, is kind of the ImageNet for RL. It gave us an interesting set of tasks with an RL interface, and with enough computation, again, it's slightly interesting. And the last bit, of course, is some new tricks. So just as learning, training neural networks requires some tricks and know-how. You need maybe even more to reinforcement. And when we have all three together, I think now we're seeing deeper RL. So this slide is a few years old, and back then you could maybe sort of fit the most exciting applications. Sergey Levine's work, real robots. But then after AlphaGo, things have gone crazy. I can't fit it. Is deep reinforcement learning any different from deep learning or from RL? So there are definitely, I think, big and important differences from deep learning. So for one, by deep learning, I mean sort of standard supervised, maybe unsupervised. So we don't have supervision reinforcement learning. So we're not told which actions to the agent has to interact with the environment, and through rewards, which can be very delayed, it has to figure out what the right actions are. So this is the main difference that also applies to reinforcement learning. The second important difference is, well, okay, now we have a non-stationary problem. So data is not I. So if we want to do, we want to train neural networks with RL, now most of the theory is out. So it's hard enough to prove things about neural nets, but once your data is on IIT, on stationary, there isn't much that we have. And in terms of actually practically training neural nets, they don't like on-stationary, so there are practical issues. How do you train state? But the data distribution isn't just non-IIT, it's, I would say, even worse than that. Distribution is in large part determined by the agent's action. So this is the exploration, this is exploitation trade-off. So you want to learn quickly, but maybe if you learn too quickly, you'll get stuck in a local minima and explore. So how can we deal with this? And if we look at what's happening in supervised deep learning now, there is somewhat of a belief, some theory to support it, that actually maybe local minima aren't such a big deal. Maybe in deep convnets, most local minima are approximate to good. And if we have enough data and train long enough to get to a good look, which is essentially almost the same as the global. I think in reinforcement learning, this, at least in practice, is definitely true. So because of the exploration-exploitation trade-off, we do have local minima neural networks definitely get stuck. And this is a big problem to solve. And I guess the last little bit is something that maybe held peeled back a little bit is there was this belief in RL that training neural nets with RL was somehow inherently unstable. So there were examples, neural nets exploding when doing TD learning, nonlinear function approximation. So I would say what makes DeepRL unique is really the combination of issues from RL with the issues from learning. Yeah, there are differences for both. What am I going to talk about? I've never been to one of these summer schools, and so I decided to, I guess, relatively introductory. So today I want to talk about, basically, first go through some basic RL concepts, and talk about value-based learning, and then get into the deep parts. So talk about DQN and some recent extensions. Tomorrow, I'd like to spend a bit more time looking at policy optimization, so policy-based methods. And in particular, I want to look at parallel methods for RL and A3C in particular, which is policy-based methods. And then hopefully I'll have time to talk about sort of what are the interesting research directions. And if maybe people are interested, I could also talk about some basically practical things that if you want to start doing DeepRL, what should you look out? So I think it's considered to be something that's difficult to practice, but I think it's relative to start. Okay, so I'll jump right in. So I think there was an RL intro from Andrew last week. I'll still try to go over the basics. So what is, you have an agent interacting with an environment over discrete time steps. And at each step, it takes an action, goes to the environment, and then receives observation. Action. Essentially through trial and error. So the reward is the scalar feedback signal. So what does it tell the agent? It's basically how well you're doing at time t. It doesn't necessarily mean, it's not feedback on whether the action you took at time t. We'll look at some examples of rewards on the next slides, but it's really about maximizing cumulative total. So reinforcement learning is based on this so-called reward hypothesis, which is not definition. So the reward hypothesis is that any goal can formalize the outcome of maximizing. And again, this is a hypothesis. Learning through rewards seems extremely general, so I think for now it's relative. I guess I forgot to say, if you have questions, please. Budget. What are some examples of rewards? So maybe you want to train a helicopter to fly stunt. This was an application. So what would the reward be? So you could give a positive reward for following desired trajectory, negative reward for crashing. You may want to defeat the world champion at backgammon or Go. So here, you would give a positive reward for winning a game and negative. So this is a good example, basically, of how general the reward setup is. At no point is the agent being told what their action is. But this is really, did you win or lose? From this, you hope to learn strategies and the right sequences of action. So you might want to make money with RL. So how would you manage an investment? Well, you might want to define the reward as being proportional to change in bank. So I think I'll put this in the past. You might want to control a power station. So again, positive reward for producing power, but there are physical limits on certain things, so you might want to negative rewards for safe. And an application like this, I think, is a good example of designing good rewards as a problem itself. In terms of long-term research, one interesting area is basically, well, AI safety. So if you give a reward to an agent and it maximizes it, how can we make sure there aren't undesired consequences? So this is a really difficult step. And you might want to make a humanoid robot walk. So you could give a positive reward for forward motion and upright. To say, forget the part of being upright, the agent might turn to crawl. And again, if you're dealing with a physical robot, then you just give control to an RL algorithm, it might break. We saw it video earlier. So you might want to include the negative cost for the strength of the control minimized towards so. And yeah, one final one is Atari games where it's proportional to the change in scale. Okay. Okay, so a few basic definitions. So the history at time t is the entire sequence of experience the agent sees. So this includes the observation at each time step, the action by the agent, so this is everything the agent gets. So observations, actions. The state is a function of the history which determines what happens next. So not everything is quite relevant for what happens at the next time step. So in the fully observed environment, the state would be just a function of the current observation. So that means we can essentially throw away everything before time t because everything is present in the observation. And the notion of a Markov state is also quite. So a state is Markov if conditioned on the state at time t. The next state is independent of all the previous states, so that all the information required to generate the next state is present in the state of time. And there is this, well, there are different notions. So we can talk about the environment state. So this is really, you know, if we're looking at an Atari game, it might have internal state variables which are in present observation. So that determines the next frame. There is also the notion of agent state, which is different, which is basically what the agent decides to store internally based on observations. So in a partially observable environment, the agent might want to store some function as it's to essentially approximate the, or infer the environment. So MDPs, Markov decision processes, basically environments where all states are marked. So you've probably seen this already, but again, you have a finite set of states and a finite set of actions, and the dynamics are determined by a state transition probability matrix of one time step next, along with a reward function. And there we have a discount factor graph. So that's somewhat important and maybe worth discussing. So in an MDP, the goal is to maximize future discount rewards. Future rewards in the future are discounted by now. So why do we do this? Well, one reason is this is mathematical. So if discount is less than 1, then basically avoid future. And that makes a lot of things work out. Also, there are some reasons to believe that well, basically there is experimental evidence that animals and value need for nature. So this is somewhat natural. So what are the components of an RL agent? So an agent typically includes at least one of the following. Policy, which determines behavior, value function, which essentially it's a way for the agent to evaluate states and actions. It's how good each state is. And a model of the environment. So you may want to learn a model of the environment. We won't be talking about models so much, but policies and values. So again, we've looked at policies already. A policy is a mapping of state to action. And policies can be deterministic. So if you have a value function, for example, could always take the best action. This is known as a greedy policy. But typically, you probably want a stochastic policy. So an epsilon greedy policy takes a random action probability epsilon and takes the greedy action probability 1 epsilon. You could also have something like a Boltzmann distribution based on analysis. So something that's interesting is that in certain types of domains, the optimal policy has to be stochastic. So on the left here, we see an example of a fully observable. So the agent starts somewhere in the maze and has to get the goal. Here, the optimal policy is deterministic, just follows the shortest path. So on the right here, we have an example of a partially observed environment. So the agent's state basically includes information on whether there is a wall to the left, to the right, above it, or below. So if that's the agent's observation, then, or the agent's state, then it can distinguish between these two gray states. So here it doesn't know if it should go left or it should go right. In such an environment, the optimal policy is stochastic. So in these states, you would basically go left or right with equal probability, and if you get to this state, go down. So here you need stochastic policy for optimal behavior. But maybe this is somewhat tried. Okay, so then value functions. So value function is a prediction of future reward for a specific policy. It's the fact that it's for a specific policy is somewhat important. So the value of a state, yes, is how much reward you expect to get follow policy 5 state at. And the action value function QSA, basically how much reward you expect to get if you take action A and state S and then follow policy 5 for the reward. So more formally, it's the expected discount return, given that you've taken action A and state S, and the expectation is over again the dynamics of environment and policy. So the action values follow a very useful decomposition, which is known as the Bellman equation. So if we look at the definition of an action value, we can basically see that this term here is essentially just the expression for the action value times gamma, but starting at time t plus 1 instead of time t. So that means we can rewrite the definition Q pi SA as this expectation, where we have the reward at time t plus gamma of the Q value for the next state, the next action, which are random variables and the expectation with respect to policy and environment. And similarly, we have a similar decomposition state values or values. So again, because we're interested in maximizing rewards, you might be interested in behaving optimally. So there's this notion of an optimal value function. So if we maximize values with respect to the policy in each state, we get what's known as the optimal value function, Q star. So for MDPs, there's a unique optimal value function, which is very useful. But it's important to note that there isn't necessarily one optimal policy. So if you think of a rectangular maze, or maybe not a maze, but a grid world where you have to get, say, from the top left corner to the bottom right corner, and there are no obstacles, there are basically many shortest paths to take. And each of those shortest paths could be an optimal policy. So there are many optimal policies, but the optimal value function, so it captures all all the shortest paths. So if we have the optimal value function, then we can extract optimal policy by simplifying the respect. And just like with action state values, the optimal value function Q star also follows a Bellman decomposition, so where we have a max over actions because we're active. So this is a very useful identity, which basically can give us algorithm learning. Okay, so given the basic definitions, again, how do we actually do reinforcement learning? So there are sort of three basic types of approaches. So there are value-based approaches to RL, which essentially try to estimate the optimal value function star. Then, of course, there are policy-based approaches, which you've also heard about. So because it might be easier to find a good policy than to estimate the optimal value function, you can search for a good policy directly. So policy-based RL, you're searching directly for the optimal policy by star or an optimal. And in model-based RL, you may want to learn a model of the environment and then plan it with respect to this model to take your action. So as it stands right now, model-based approaches have not been as successful in rich complex environments. But I think there's a general belief that learning models will be extremely important. And I think, yeah, this is one of the very exciting directions. Okay, so today we're only going to look at value-based methods. So look at Q-learning specifically. So how does Q-learning work? So we're going to assume we're in an MDG. So we have a finite set of states and a finite set of actions. So we can essentially represent the action value function as a table, and we can start with the guess for each action value. Could be 0, could be something. So then we can interact with the environment and start collecting copies of experience. For each one, it's essentially state and action, the following rewards, and the next. So for example, we act with epsilon greedy policy with respect to this Q function. So what Q-learning does is essentially turns the Bellman equation into an update. So what the Q-learning update is doing is changing your current estimate of the Q value towards this target, which is the reward you got plus gamma times the maximum Q value at the next state. And this is essentially turning the Bellman equation optimal value functions into So because we know that the optimal value has to follow the Bellman equation, we're essentially making our estimates closer, ones that will satisfy Bellman. So for MDPs, under relatively mild and very reasonable assumptions, you can prove that Q-learning is guaranteed to converge to the optimal value function star. This is kind of amazing because MDPs are very general, and we essentially have an algorithm that is guaranteed to find optimal value. So what are the conditions? So the learning rates alpha t have to follow a certain schedule, basic standard conditions for stochastic optimization, so they can't decay too quickly. And the other important condition is ergodicity. So you have to keep visiting every state, taking every action, otherwise you won't get optimal. So if you can satisfy these conditions, then you find optimal value. And in sort of small discrete domains, epsilon greedy, epsilon random exploration can explore reasonably efficient, basically does satisfy the ergodicity. This tends to work well in practice. So why isn't this the answer in RL? So of course, most interesting problems don't have small sets of discrete states in action. So what do you do when the state is continuous or when it is very high dimension? So this is where things get really interesting. We can't keep a giant table in memory, so we use a function approximate to parameterize your Q function using some parameter vector theta, and then you can do Q-learning with that. So I guess the dominant approach to function approximation was a linear function approximation at one time, which is basically defining your action value function Q as a linear function of some set of basis vectors phi. And the coefficients in the linear combination theta are parameters. So an example of this is the famous mountain car problem, where you're controlling this car and the goal is to drive it up the mountain, but the engine's not powerful enough to go up the mountain. So what you have to do is basically first back up and then accelerate down the mountain to get to the top. So this is a continuous state problem where state is, for example, the position along the x-axis and the velocity. So one popular approach to function approximation was coarse coding or tile code. So you could, for example, cover your state space, so velocity, position, with a bunch of circles, and whenever you are in one of the circles, this feature will 1 or 0 otherwise. And you can do Q-learning linear function approximation with the set of features. Of course, this doesn't scale well to higher dimensions. So for example, what can you do if you want to learn to drive a car, this video, learn to drive this toy car around the track. Basically, if you do any kind of tile coding, the number of features will be exponential in the number of dimensions, and this isn't going to work. So it's not much better than what we had before in the table. So again, these kinds of approaches were fine for relatively low dimensional problems, but they suffered from the curse of dimensionality. But for a long time, this is essentially the setting that most of the field person finds. Perhaps the main advantage of linear function approximation is that you can still prove certain results about such function approximation. So you could prove convergence of P-learning, I think P-learning said. But basically, to tackle really interesting problems, we need more powerful functions. So this is, of course, where deep learning comes in. The successes of deep learning have been in basically being able to train very rich and powerful functional approximations, high-dimensional. So starting, perhaps the first really big success of deep learning was the work of speech recognition, George Dolgeff, and then the now famous ImageNet results. So this covers modalities of speech and vision. More recently, it's been expanding into, say, natural language processing, text processing. So now the best translation systems for text are essentially giant recurrent neural networks. So deep learning has been very good at being able to learn very powerful function approximations from all kinds of data. So this is, I guess, the main motivation behind deep reinforcement. Let's use these rich function approximations and neural net specific. But of course, it's a trade-off. So now that if we want to use neural nets, we could, at least for now, we have to give up on product. So even P-learning with the neural net, I don't think there are good convergence results right now. So if we want to build systems that perform well, maybe that's a reasonable trade-off right now. Maybe very catch up. But philosophy behind DeepRL is, take your policy value function or model, represent it with the neural network, then optimize it end-to-end. So optimize the overall performance of the system end-to-end gradient. Now the real question is, can we actually do this in a stable and efficient way? Because we know it can get very long, diverge. Okay, so now I'll talk about DeepQ networks or DQN. That's something. So the high-level idea behind DQN was basically to try and make reinforcement learning look like supervised learning, because we know that works, and we know how to develop it well. So we started with Q-learning because it was essentially the simplest method that we knew worked, and people had used it in the past with neural networks. So the idea is to take the Q-learning loss and just optimize it in a batch stochastic gradient. But of course, there were examples of divergence. So what can we do to make this problem more stable, more like supervised learning? So the first change was, or the first design choice was to use what's known as experience free. So instead of doing learning purely online, whereas, say, the agent is interacting with the environment, getting tuples of state action, rewards, next state, instead of doing updates on the data as it comes in, we want to smooth out distribution. So this online stream of experience is very correlated. So at any time, your current state and your next state are very similar. And as the agent is exploring the environment, it might go one area and then move to another area and get stuck. You're essentially getting these very low correlated samples of experience from different parts. And we know this is exactly the kind of thing neural networks don't like and aren't. So the idea of experience free, which was actually used 20 years ago, is to put your experience into a giant buffer as it comes in. And to do learning, you just sample mini batches from this buffer. So now when you sample from this giant batch of experience, you're more likely to get a sample that's more evenly distributed through your state space and action space. So in the past, it was used mostly for better data efficiency, because computers were slow, and if you're interacting with simulators, simulators probably also very slow. So by reusing old experience, you could basically save on interaction time with environment. But perhaps the main difference in how we used it was to really say, well, it actually makes the problem look a lot more like supervised learning, stabilized learning, in addition to safe interaction. The other idea was to basically, again, make the Q-learning problem even more stationary. So we introduced the idea of what's known as a target method. So here we have essentially the Q-learning loss, where again, we're updating the current estimate of the value of state S in action A towards this target. And in standard Q-learning, you would have your parameters, current parameters theta I, both in the thing you're updating and in the target. But what ends up happening is, for example, if you get a big reward, you will increase your estimate of the current Q value. And what this will do is also probably increase your estimate of the target action value. So I have a demonstration. So for example, we have these are two consecutive frames from the game of Space and so as you can see, they're almost the same with the few small differences where this laser hit the alien and it's starting to disappear, and this laser is moving. So because neural networks, their inductive bias is thought to be to smooth functions. So when you apply a neural network to these two inputs, you're likely to get very similar outputs. So when you try to increase the value of the USA, you will also probably increase the value of the next state. So when you come back to this data again, you will have a higher target. And because of this, the agent can end up, or the network can end up essentially blowing up for chasing itself. It's coming up with ever higher targets for the current value. So the simple trick to partly solve this problem is to use a different set of fixed parameters for the target. So what we do is essentially periodically take our current weights and copy them to the target network weights, which are denoted by theta minus. And now what happens is, as you increase the value of QSA, the weights for the target are fixed, and your target doesn't go. So now it's starting to look a lot more like standard supervised learning from a data set, where you're sampling many batches of experience, and you essentially have fixed targets for periods of time. And every once in a while, you want to update the target network current. Okay, so now we can essentially describe the entire training method for DLN. So we initialize the weights and target network with some set of parameters data, and then the agent essentially starts interacting with the environment. So it takes action A and gets a reward in the next state, but instead of doing an update on this data, it goes directly into this replay memory buffer, which we denote by. And to actually do the learning, we sample many batches of experience from the replay memory and essentially do an SGD mini batch update on the Q-learning response with the target network trick. And then periodically, we want to update the weights of the target network. So you're actually learning to get more and more experience. Okay, so what does the whole system actually look like? So again, we're learning a Q function, and we're parameterizing the action value function using a convolutional neural network. So the input to the network is a stack of 4 previous frames from the game. So this again goes back to this discussion of history and state. So Atari games are not fully observable. So we want to include some history, for example, so that the agent can see which way the ball is moving. So this is not very general, but it turns out that using just a small number of recent frames is enough context for the network to play. So then it goes through several layers of convolutions, and there's a fully connected layer. All the nonlinearities are preludes, which again have a discontinuity, which is scary, but they do work in practice. And finally, the network outputs the action values for the different actions. So we applied this to, again, a set of, I think, 49 Atari games at the time. And the main result was that, one, it drastically outperformed sort of the dominant approach at the time, which was linear function approximation and design. So here we have games on the x-axis and the percentage of human performance that the two methods get. So blue here was the original BQN, and gray was linear function approximation. The vast majority of games, BQN is better. And the other interesting thing was that on more than half the games, DQN reached at least 75% of human performance. So this was the really exciting bit, that there were many different computer games which we didn't handpick, and the single network architecture with the same hyperparameters learned to play them in a level comparable to essentially a good human game player. So the human results here aren't sort of the highest scores achieved by the world champion at the game. The human results are one game testers, quite good at playing games, playing all. So the goal here was to get a system that was really general. So we're not trying to beat the world champion at every game. We want something that does well across many tasks that the human might find interesting, which is really getting back to what we think intelligence is. Now, of course, by now these scores are not very impressive, and they're much better systems. We'll look at some later on. So you can look at some videos. So this is a demonstration of the original BQN system playing this game. So it was extremely good at games that required essentially very high frequency reactive control, which is maybe not that surprising because it's doesn't have a problem with reaction. But there were some more interesting games, so we'll get back to sequence in a minute, where it basically learned to, say, sacrifice short-term rewards for more long-term. And so driving, again, is an example of something I was good at. Now, this is a very simple driving game. You wouldn't want to put deep in an actual car. But it learned to drive in a relatively aggressive style, but learned to slow down on snow, which was exciting. Again, you might see a pattern here that games involving shooting quickly enemies, it seems to be very good. Sorry? River raid is elite. Oh no. Okay, I won't show it. Alright, so Space Invaders. We'll look at this one in slightly more detail. Yeah, I'll have to take note of the river raid. Right. So boxing, again, I think it's controlling the player on the left, so it learns in the opponent. So Breakout was fun because it was sort of, Pong was the first game where defend worked well. Breakout took a little longer to get work, but it was really exciting to see the agent basically learning to break through and let the ball bounce on its own, which is actually really hard to do in the simulator. So it's quickly much better than well, really all of these games. Okay, so how is the network actually playing these games? So this is perhaps a very basic example, but might still be worth going. So again, here we see the agent playing Pong, and the trajectories are superimposed. The agent doesn't actually see them. And what we see here are outputs of the network's action values for different actions. So cyan here is do nothing, purple means go up, and pink means go down. So at this point, we see that the agent is outputting a high positive value for all three actions. So it's essentially saying, I think I can get a point here, and it doesn't really matter which action to take. Maybe it's better to go up, but you're going to get there anyway. So actually, wait, no, let's go down. So basically, there is some noise. Again, get back to this thing. So if we fast forward a few frames, so now if the agent doesn't go up, it's going to lose a point. And now you can see this in the action values. If you stay or go down, you're very likely to lose a point, so you better go up. And again, it continues. It looks like the agent is going to lose this point, but actually the trick to playing Pong is to hit the ball with the side of the pad to make it go really fast. So this is the behavior that it learns, and it essentially learns a shot that the AI can't learn. And again, here we see that the agent's about to score a point, and it's reflected in the action value. So it's all essentially now it's fun to look at a few more examples of learned action. So again, here the agent is playing Breakout, and we see the predicted state value function, which is basically the maximum Q value at each state. And here we see Q values all the action. So again, what's interesting is that with Q values, they're at most points in the game. It doesn't matter which action you take. So here the ball is going up, so the agent can do anything. But the Q function has to represent this. So that we'll talk about policy-based methods tomorrow, but I think this sort of shows why learning a policy might be easier. So if you're learning a policy, you don't have to predict the correct values here. It actually doesn't matter what you do at all, because the ball is going up and you have time to get one. But with Q learning, the system has to learn action values correctly so that it can get correct values for previous state values. And we sort of see that the action value goes up as the ball is going up, and then when it hits the brick, it falls off and then starts going up again. And here's the same thing in space and iterative. So again, here, this is what we call mothership. So it's worth way more points than any of the space indicators. So when it appeared on the screen, predicted state value started to climb. The agent tried to shoot it down. But because it missed, the estimate of value went down. That's drastic. Right. Yeah, so we haven't done this so much on Atari, but other environments. Um, Basically, yeah, like you say, in parts of the game where it doesn't matter the agent does, it just jitters probably because of the noise in the Q function. All the Q values are roughly the same, but because of the noise at any given frame, one of the actions might be there. And yeah, if you give it a penalty for taking actions, it will uh, prefer the do not. So here again, you can see two fields, and now it hit the mothership. So it anticipates these big rewards and sort of knows when. Right, so I mentioned the game of Sequest, which I think is a particularly nice example. It took a while for John to okay at this game. So the goal of the game is actually not to shoot the fish with the submarine. It's actually to pick up divers. Because if you have a diver, you can go up to the surface and get more oxygen, and then you lose the diver, but you can keep playing the game on. So here we see that basically the agent is playing the game and its oxygen level is going down, and sort of see that the action value function is very slowly drifting down. And eventually, here we see that it stopped shooting the fish and went up to get oxygen. You get no points for going up to the surface, but you get to play longer. So this is, again, an example of where the agent sacrifices immediate rewards to get more long-term. So this is really the heart of RL, that you can learn these sorts of things without per-action supervision. Yeah. So basically, yeah, should have mentioned but the rewards were defined as basically the change in score in the game. It's like no one, but everything else, it has to get like oxygen. Yeah, that's true. So yeah, we do still keep it in. So the human, I guess, yeah, doesn't. Well, the human probably doesn't care about score specific, which is that's another interesting discussion. But what is the human actually? But I guess here it's not a perfect comparison to humans, but yeah, the level of supervision is still not our action. So, yeah. Yeah, so here all the hyperparameters were fixed all game. So I think it was like updated every 55 frames or something. So yeah, if you want to play with DQN, the source code was released paper and it's available at this link. Now DQN runs on a GPU, so it's probably need a GPU to experiment with it. Might still be interesting to look at running it on simple problems, but now there are much more efficient reinforcement learning in terms of specifically ones we'll talk about. So yeah, I think one interesting thing to look at quickly is, haven't people been training neural nets with e-learning for many years? Like, is there actually anything to that? So yeah, we can look at two successful uses of e-learning. So one is this neural fitted iteration algorithm from Bart Friedmiller. Is at Freiburg, so not far, and also at DeepMind now. So he had this method for training neural nets with Q-learning since 2005. So how does it work? So the idea behind neural fitted Q iteration is actually quite similar to stabilize the learning process by making the targets fixed. So the way NFT works is it iterates, which alternates between running the current, say, epsilon greedy policy and collecting more data. And then, so basically at each iteration, you train a new Q function from scratch. And the data you use to train it is basically the data from all previous iterations where the targets are computed with Q-learning with previous Q function. So at iteration I, you'll take all your data and compute all the Q targets with your previous Q function. And now you do a batch gradient descent learning RPROP on this whole data set. So you essentially, if you do n iterations, you have to train n neural nets from scratch. And they found that basically, if you don't reset the neural network, it doesn't work quite fast. So this works quite well with relatively small neural networks where you train many copies. With convolutional neural nets, where you might train for hours or days of GPU, you could probably still do this, but maybe you don't want to retrain the network. But actually, DeepYon can be seen as an online variant of GPU. So you don't restart the training at each iteration, and we don't sort of update the targets on all the data, fix them the same way. So it's essentially doing both online, where you have a buffer of experience and your periodic recompute targets while training one neural net. But this is very much an inspiration for DeepYon, and actually the target network trick came about after thinking, why doesn't it follow up training? Now another even earlier example is the work of Wang-Ji Lin. So his PhD thesis from 1993, RL for robots using neural networks, had a lot of great ideas. So again, he was the person who, to the best of our knowledge, introduced experience reading. And again, he trained neural networks with Q-learn. They didn't seem to diverge. So what was the difference there? So in Wang-Ji Lin's architectures, he used a separate neural network for each action. So for each action, there was a network which takes the state and has only one output, which is the value for that action. As you remember in DeepYon, we want to train a big and powerful neural network, and it's hard enough to train one concept. We don't want to have n concepts for n actions. So DeepYon outputs n actions from one network. But because these neural networks are separate, you essentially get this target network trick for free, where if you increase the value of one action, there is no interference with the values of other actions, because they're entirely different neural networks. So this is a way of, again, getting some of the benefits of the target network, separating out parameters. So the less interference there is between parameters of different action values, the fewer problems we'll have, explosions of weights. But again, it's a trade-off. If you're training a relatively compact model, maybe this is fine. Maybe it's worth going through this quick. So one question that people have looked at is, well, again, what is the network actually for? What kind of representation is going to discover? So we're going to look at what's known as the T-SNE embedding feature vectors. So probably don't need to explain it in detail, but it's basically a way of visualizing high-dimensional data by projecting to two dimensions. And it's similar to multidimensional scaling, which, for example, tries to maintain pairwise distances. But what t-SNE does is it tries to keep points nearby if they are nearby, but because it's impossible to maintain all possible distances, it allows for some neighbors in the high-dimensional space to be far apart below dimensions. So when we look at the t-SNE plot, if 2 points are nearby, they're probably similar in the high-dimensional space, but if they're far apart, it doesn't mean that they're different. It could still be similar. So here we have an embedding of the agent's experience from playing Space Invaders. So we let PQN play Space Invaders for a long time, and then we took all the feature representation, so the last hidden layer of the network, embedded them and projected them down to 2 dimensions with t-SNE, and visualized them where the color shows the predicted value of each state. So we can see that basically PQN learns a representation where states with similar values seem to be projected to similar representations. So sometimes this means that the states are similar in the high dimension, so they're very similar inputs. So for example, here we have somewhat similar configuration of aliens, but these barricades are gone again here. So it learns essentially sort of value dependent. So others have looked at, done similar analysis, different games. And the work of the Zahavi, so they're arguing that PQN essentially learns a hierarchical state aggregation, and that it actually learns an implicit hierarchical policy. So they did a similar embedding for Sequest, where here it's colored by state value, and here it's colored by the amount of remaining oxygen. And they found that there is basically this part of the space where an agent is following a specific policy as the oxygen is going down, and then it's essentially teleported here, which is the so-called option for you to see the oxygen going up. So, okay, so now I guess I have maybe 10, 15 minutes left, so I'll talk about a few recent extensions of one interesting thing with Q-learning is that when you're using a function approximate, Q-learning, we take its maximum over actions of this approximate Q value. And because it's approximate, there is noise. So, for example, if you add Gaussian noise to your Q values, sometimes this will be a positive number and it will make the estimate higher. So when you approximate maximum by taking a max over noisy values, you will actually tend to overestimate the true value. And this actually does indeed happen in PQ. So the idea behind double Q-learning, which is the work on Adam Castle, is to use the regular and target weights of the neural network in another way to reduce the bias. So the double DQN loss, so instead of having a maximum in the target over actions, you actually use the regular weights to do the argmax to find the best action. And then you plug it into the target Q function to get the actual value. So now use one set of weights to find the best action, and then another set of weights to value. So because the weights might have slightly different noise, you actually will end up with a more accurate, less sort of overestimated estimate. And this actually works really well in practice. So here are some plots where x-axis is training time, and the y-axis is the average action value predicted by n and by double DQN in a number of games. And this is log scale. So we see in DQN that basically you end up learning sometimes very high Q values and start diverging, like in the examples here. But double DQN sort of learns much more sensible, much more Q value. And this is not just sort of curiosity, because policy is based on Q values. This translates to better performance. So maybe the precise metrics don't really matter, but basically see compared to DQN, whatever the metric, it's much higher. So this is a nice way to reduce the bias in this powerful function. Right, so another very nice idea is to basically make better use of their previous experience. So replaying all transitions with equal probability is basically highly suboptimal. So why is this the case? So maybe when you start playing a game, all your Q values might be close to 0. That's how neural nets tend to be initialized. And then you get a few rewards. So which transitions should you replay? Most of them are essentially, you have a zero Q value, you have a 0 reward, the next state is a 0 value. So if you keep replaying that, it does nothing. You have sort of bad estimates of the Q value, you're using it to learn. It's not doing it. Of course, you should learn on the transitions where you get the first few rewards. So this is the idea behind prioritized experience rate. So this is work of Tom Scholl and others, also from DeepMind. So they prioritize by essentially the absolute Bellman error. And this leads to, again, much faster learning over pretty much all games. So at the beginning, you will focus on the transitions where you had reward and sort of progressive, sort of keep training transitions where still right. So the last idea is this dueling DQN paper, which was, I think, the best paper, one of the best papers at ICM last year. So there is this notion of an advantage in enforcement. So if we define the value function I, state value function, so there's what's defined as the advantage is essentially Q value minus the state. So in the greedy policy, this will mean that the advantage of the best action is 0, and the advantage of suboptimal actions will be negative. So why is this interesting? Well, basically this shows that when you're learning a Q value, there are two things to learn. One is the overall value of the state, and the other thing is sort of, well, what difference the actions of the state actually make to the future. And you can embed this knowledge into a neural network architecture. So here we have, again, standard DQN where you have some convolutions and out value. So what you can do is basically you still have your convolutions, and now you, before you predict Q value, you have two separate channels, where the first one will just predict a single number, which we will call V. The second one will predict, again, one number for each of your actions. And the output will be just the sum of this and the single. And the hope is that the network will tend to capture the value of the states here and the advantages here. So if you do that, it's not actually enough. It doesn't help as far as I know. So the main innovation in the dueling network architecture is to remove the extra degree. So if you simply do this dual channel thing, it can still capture the value in these things that you want to be the advantage. But what you can do is inside your network, you subtract the average advantage value from the advantages and add it to the value. So now essentially, the network is essentially forced to use that single number to present the value because it doesn't have the same degrees of freedom. And you can still backpropagate through the entire system because it's just summations, arithmetic operations. And this, if you're doing any kind of learning with a neural network, I find this pretty much always works better. And the results they had on Atari were very impressive, combined two previous tricks. So, nice visualization of whether it's actually doing the right thing. So here, it's again DQN playing Enduro, the driving. And what is being shown on the left is visualization of the gradients with respect to this value estimate. And on the right, it's a visualization of gradients with respect to the advantage. So we're essentially asking which pixels do you need to change the value at the state, and which pixels do you need to change the advantage. So for the value, it pretty much is tracked where the road is going, presumably sharper turns harder to do. But for the advantages, it pretty much lights up when it has to pass a car. So it actually really seems to capture the difference that in most states maybe doesn't really, for the value, it doesn't matter which action press you're just more. But when you're behind another car, basically some actions have very different value. So basically this architecture really does capture this aspect, advantage. So that was everything I wanted to cover today, and I think
So, for instance, like if you had a game where you had like reward only at the end, it was a very long game and you only had reward at the end, like converge easily, like you just start with a random policy?
I mean, I guess it depends how hard the game is. So it depends on your exploration. For example, Pong is an example of such a game where so each point is essentially you either get a point or you lose a point whenever ball gets scored. So in Pong, this epsilon greedy exploration, we start with a high initial epsilon value for all games. So in Pong, if you take uniformly random actions, you will win something like 3% of the games. So this is enough for it to essentially bootstrap and learn how to play the game almost. If purely uniformly random action selection will win no games, then there is no hope learning. So basically, it depends on whether your exploration will sometimes win a. So something like AlphaGo, for example, what's interesting there is, or I mean any two-player game, when you're doing self-play, there is this sort of natural notion of the curriculum. Like if you try to train AlphaGo by playing against like the world champion every time, like it would never win with purely random exploration. But when you have a network play itself, it starts off being really bad, but it, half the time it will beat itself. And one copy is going to win. So that essentially provides a natural curriculum where it starts learning easy things. But playing against an emulator, you basically want your explorations good enough to get some points.
About generalization, so how much do these networks generalize? Is it starting from minimal changes, like I don't know, just changing the color of the ships in the Space Invaders, or maybe starting from a configuration with one row less of ships or something like this?
Yeah, so it's a good question. Yeah, so I go back. One way in which we tried to look at this was so usually when we evaluate, at the beginning of the game, the environment forms a random number of like mellow factions, which do nothing, but essentially, it's essentially like starting with a random seed PM. So Atari is deterministic, but sort of humans always play at a different rate. So doing a random number of these actions sort of might make the enemy come from a different direction. But it was still essentially close to deterministic. So the other condition which we look at is this human start, where now DQ1 doesn't start at the beginning of the game, it starts at randomly sampled states from human. So this does test basically whether it can play states that it hasn't seen. And sometimes it can, sometimes it. So I think different configuration of aliens and Space Invaders should be able to run. But like if you randomly change the color, it's okay. It gets a grayscale, so that would be okay. But if you trained on the color input and then permuted the colors, it would pretty much break. So there is some generalization, but like it's not magic. It's really something it hasn't seen at all. Do strange things. So you can try to make it more robust by adding noise during training.
I don't know, like adding 2 pixels on both sides of the ships, like would it break it? And if it breaks it, how long does it take to make it recover?
I mean, I don't know if we've done these exact tests. I think it would recover relative. I'm trying to. Yeah, that's sweet. Yeah, maybe nothing that's adversarial. I think there is some recent work on actually adversarial training, and well, not adversarial training, but finding adversarial example agents. So they looked at like how can you change the inputs to make the policy do whatever you want. From what I remember, it's relatively easy to make an agent do whatever you want by adversarial changing. But this is sort of similar to a concept where make it ostrich, small change. But it's, with all of these things, it's like if you want it to be robust to certain things, you should include it during training. And otherwise, it won't really. But maybe we can have, almost certainly, we can come up with better algorithms that sort of penalize the SCM, something like that. So avoid spurious changes. But DQ1 is susceptible.
So how long does it take until you have seen like every state?
So, okay, with BQN, we trained it for, so in terms of time, it was like 10 days in a GPU rough, which was 200 million frames. I forget how many, I think that's months or years of real-time play, so it's a lot. And it definitely doesn't exhaustively cover the state space. So when we do evaluations of human starts on some games, DQN finds a policy that it's happy with, which just plays one way, but a human plays in a totally different way and breaks it. So it definitely doesn't have like the full. I guess another reason for that is we reduce exploration during training. So epsilon goes down because I think basically for key learning to converge, you eventually need to reduce exploration, or key values might change, but it definitely doesn't have the full.
Hi, so for a fixed game and fixed hyperparameters, once you've done the training, is there any guarantee or any statements you can make about the optimality of the result or the consistency of it? For example, as a confidence interval or something.
Not really. I mean, definitely nothing about optimal. So this might be disappointing. But I think for now, this is the trade-off that even for supervised learning, I think theory is still catching up. Once you add control, like I really don't know if any strong here. It would be, very interesting because we start building more and more powerful systems. You can want to have guarantees, want to do crazy things to material. So I mean, that's why I say it's important. People should, but it's a really